Okay, show of hands again, really quick. Who has a background with multi-level models, panel data, longitudinal? I'm not gonna cold call on anyone, so you can raise your hands. Decent number of people? Okay. Even for the people who do, at least some of these terms are gonna be very, very confusing because I am pulling from a bunch of different fields and trying to give you a common language to understand a whole bunch of different problems that range across the social, behavioral, and health sciences and policy. Part of the problem with that is they developed kind of asynchronously and have very, very contradictory language, which we will take on, head on and try to explain in a kind of coherent way. So hopefully by the end of this, you will maybe not be too shell-shocked because it is a lot of information. But at the very least, you'll have a sense of where to go in the future. And if you want to take my class at ICPSR, it's a much more elongated version of this talk where I get to actually go into some nuance and some depth. Any questions before we start? No? Okay. So just a little bit of an overview. We're going to talk about kind of what we're talking about first. We're going to talk about the Tower of Babel. Then we're going to talk about some demons. We're going to talk about how to kill them. And then we're going to talk about how you can avoid being a sheep and just doing what you're told. And instead, do what you should be doing that's relevant to your actual problem instead of what a book tells you. Because fair warning, the books are written in a very specific context that probably doesn't apply to you. So basic models are going to all assume that data are conditionally independent. What that means from your first semester regression class is once you put the stuff in the model, once you put the variables in the model, the stuff that's left over should be random noise. It shouldn't be affecting the other things in your model. Most of the data that we actually, do I have a pointer? I do have a pointer, it just doesn't show up on here. Most of the data that we actually deal with as social scientists, behavioral scientists, pretty much anyone, especially anyone who studies people, the data are clustered. And what that means is we are almost automatically violating conditional independence. The most basic tenet of statistical models is invalid for most of the data that we actually apply it to. So think of people. People can be in the same place. They can be under the same government. They can interact with one another, as we are ostensibly doing right now. They can be exposed to the same things. You were about to be exposed to my rantings on multi-level modeling. They can exist under shared, lived experiences. Is this a practical problem for us, though? Most of the data that we've got are inherently clustered, they're inherently nested. But why is this a problem? Well, maybe it's a problem. It's probably a problem. It is definitely a problem. Just fair warning, you're not gonna sleep very well tonight. Why is it a problem? Basically because of omitted variable bias. The conditionality or conditionally independent assumption that we're all taught very, very early on in our statistics careers is really about omitted variable bias. It's about leaving stuff out of the model that should be in the model that can moderate or mediate other effects, that can modify your beta coefficients, that can modify your standard errors in some way. That leaving it out of the model is really problematic for making actual inferences. That's all of this talk. That's something that crosses pretty much all social science, behavioral science disciplines. It is something that is inherently problematic with everything that we do. There are a bunch of ways to deal with this sort of problem. You're familiar with some of them. You may not be familiar with all of them. Some of them just aren't taught in certain disciplines. We could go with spatial models. We could go with network models. We could go with panel data models if you're an economist. Longitudinal models if you are a psychologist or a biostatistician. We can go with hierarchical models if you are from education. Many of these things, most of these things really can just be collapsed under a broader kind of inferential framework for mixed effects models. That's going to become clearer the longer we go through this. But in general, a bunch of things that are taught in very isolated silos, in very different ways, can all be subsumed under this. And they're all basically about trying to answer similar questions and solve similar kinds of problems with admitted variable bias. Practical advice on which models to apply, on what to do, varies quite a bit and is very contradictory. You may talk to different people on your committees and they just tell you completely different things. I've had the wonderful joy of having two books open at once and they ostensibly contradict one another. One was written by an econometrician, the other was written by a psychometrician. They're theoretically at least talking about similar data structures. They're talking about something being measured over time at repeated intervals, and they're saying to do the exact opposite of one another. That's more common than not in applied statistics, and it's not really ever addressed in a practical way. We're going to talk about a little bit about how you can navigate the context in which these things are written and understand whether or not a specific piece of advice is really relevant for you or not. And I already said that. I jumped ahead. The basic reason why you get very fundamentally different kinds of advice from different fields and different books is because there are three kind of fundamental types of statistical analysis. And this is something that's a bit more meta than we usually talk about. It's something that is just kind of accepted in your field that this is what you're doing. And so when you get advice, it's conditional on you doing the right kind of statistical analysis for your field. So we can start with kind of the most common, the most traditional modeling and data generating process. You're just trying to understand how the thing works. You're trying to have a simplified model to something that's still realistic. You're trying to include the mechanisms at work. You're trying to include how you think things interact with one another. You're trying to model latent variables. You're trying to model the process itself. This is how we're usually taught regression across a whole bunch of different fields. It's just you're trying to design a model that is a reasonable representation and context for what you're doing. We never really do that great of a job at it because reality is more complicated than a statistical model, but the goal is to try and get something that's close. We can also just talk about causal inference, specifically narrowing down a mechanism. So you are trying to figure out the effect of X on Y and controlling for everything else in the model, controlling for everything else in reality that matters, and just homing in on the specific mechanism. We can think of experimental design for this. Experimental design is the canonical example of looking for a causal mechanism, but lots of different fields try to do this with observational data. If you are pulling from modern microeconometrics, they're doing this a lot. It's the reason why their models look so weird compared to psychologist models, compared to a lot of applied statistics, compared to education research, because they're trying for a different goal. They're trying to isolate a very specific thing instead of modeling the entire process. And when you ask them about this, they admit it freely. And then if you put in your question, how would I go about modeling this like an economist if I wanted to model it structurally, if I wanted to model the data generating process? They'll give you a whole bunch of different answers that are much more in line with everyone else, much more in line with psychologists, with sociologists, with policy people that are not trying to do that. They're trying to model a data generating process more generically. And then the third one that has come up a lot more in the last 10, 15 years and also tends to confuse people quite a bit is prediction. Machine learning people love this one. You are not really interested in the mechanisms, which are the overriding focus for a causal model or a data generating process model. You're just interested in trying to recreate Y. So not the beta coefficients, but Y hat. You're trying to build a model that can reproduce reality on a consistent basis. Clustering, which we started talking about, which the whole talk is about, is really going to affect each of these kinds of enterprises in a very different way, and it's going to dictate the kinds of solutions that you're going to use. It's very important to understand what you're doing ahead of time so that you can start by dismissing the things that are irrelevant to it. Modeling a DGP is usually going to require that you actually take into account group conditionality, that you try to model it properly. This is classical multi-level modeling. This is trying to understand the structure, trying to understand why people are influenced by the school that they're in, by the government that they're in, by the country that they're in. Trying to understand person-specific effects if you're doing psychological research versus common effects that apply to things like gender. So it's very important in this context to really think deeply about the broad mechanisms. You switch it to causal inference, it's either controlling for the group conditionality, it's ripping it out so that it can talk about some mechanism within it, some direct effect absent the effect of the group that you're in, the school that you're in, the country that you're in, or it's redefining the mechanism to be context specific. It's redefining the mechanism to be interactive with your environment. And they're doing that in a very specific way. They're restructuring their data in a very specific way. If you're familiar with heterogeneous treatment effects models, this is an example of that, where maybe you want what is the effect of some kind of school intervention on student test scores, but you let that school intervention vary across states or across types of communities that people are in. That's still a causal model, even though it's still factoring in multi-level structure. It's just doing it in a very specific, focused way. You're not trying to understand everything that affects school test scores. You're trying to understand whether this thing affects school test scores and get a good measure of the magnitude of the effect. And in the case of a multi-level model, the heterogeneity of the effect across different communities. For predictive accuracy, you're pretty much always going to want to do this. You don't really necessarily care about the mechanisms in this case. It's nice to understand them because then you'll understand when something breaks, you'll understand when something switches and your model no longer functions the way that it did. But in general, accounting for group conditionality, being able to put random intercepts, random slopes in a model is going to increase your predictive accuracy. Because when you don't do it, you are basically just talking about average tendencies. And if the average tendency in one school is very different from another school, and you don't put school in the model, you get the average, the weighted average of the two schools together. So your predictive accuracy, this is why R-squareds do better in multi-level models than in classical linear models, because you're able to soak up some of the additional variation in the residuals. These goals are pretty heavily interrelated. You can do one thing with the others in mind. If you're trying to do causal inference, you might want to do a predictive model for something like propensity score matching, which is literally just a machine learning algorithm. If you're doing data generating process modeling, it's a good idea to take some experimental evidence maybe and talk about kind of what things the experiments confirm are actually relevant to your data generating process and iterate between. So you can jump across these things, but the way that you structure them is incredibly important and incredibly particular to the thing you're doing. Is there any questions about that? Can everyone hear me okay? Yeah, okay. So why is there so much difficulty in understanding this? Why is this probably the first time anyone has actually unrolled this to you and explained the thing that was backing up all of your statistics education up until now in a way that explains why different fields are giving you very contradictory advice, very contradictory kinds of evidence? It's kind of complicated. We have to really go back all the way to the beginning. So once upon a time, there was a very common language for statistics. The field was very new, and words meant something specific. Why did they mean something specific? Because there were like 6 people in the world who were doing this research, and they wrote each other letters, so they knew what they meant. There was no kind of proliferation through journals. There weren't thousands of people trying to take these things and modify them a little bit to fit their own research. So everything had a common language. Everyone understood one another. Way back, we're talking 1905 to 1925. For multi-level modeling, we're talking about R.A. Fisher. R.A. Fisher taught people ANOVA. He also taught people lots of other things. He invented maximum likelihood for all intents and purposes. He was also a raging racist, and his literal job title was Professor of Eugenics at Cambridge University. So these were not nice people, but they did a lot that we still use today. ANOVAs are still used in lots and lots of research, especially for experimental design analysis. But pretty much everything for multi-level modeling can be traced back originally to ANOVA, which he didn't invent, but he kind of gathered up lots of things, and he invented a fair portion of it. People liked ANOVA quite a bit. He was the first person to write a book. It was for practical researchers, but it was for experimental design. So he was working with people like, what is his name, Gossett? Yeah, who worked for manufacturing companies. He worked in agricultural economics. Like, they were doing experimental designs to try and figure out things like, what happens if we tweak a recipe to the taste of beer or to the yield? They worked specifically with companies to help fund their research. They worked in lots of agriculture, so they were doing experimental designs on things like fertilizer. They were doing lots and lots of experiments. That's what these models were originally built to do. We move forward a little bit. Henry Chaffee wrote the first academic textbook in the 1950s related to ANOVA. It's called The Analysis of Variance, and it is the jumping off point for a whole bunch of different fields, taking these kinds of models that account for structure in clustered ways and using them. The thing is, he was writing it in the context of experimental design. He was writing it in the context of analyzing a specific causal mechanism. When you transition to other things, when you transition to modeling a data generating process more globally, so not experimental designs, but things like regression, or when you try to model, you try to build a predictive model like machine learning people do now, some of the things that he was saying in this book, some of the things that Fisher wrote, no longer hold. They no longer make logical sense. The thing is, no one told that to people who were incorporating this research because they didn't know it themselves, because that wasn't something that these people were writing. Machine learning didn't exist yet. So they weren't making the caveat. Now, when you come up with this approach that hasn't been invented yet, but will be invented in 35 years, this line right here in this equation will no longer hold. So you kind of have to infer that, and it's been slow going and really, really difficult. So way back in Henry Chaffee's book, a fixed effect was a specific group comparison. You can think of it as a dummy variable. You put men versus women in your regression model. You put Trump voters versus non-Trump voters in your regression model. That's a fixed effect. That's a group comparison effect. A random effect was a standard error correction. That's all they used it for, because it gives an experimental design more generalizable standard errors. That's the only thing anyone knew it was good for up through the 1950s. Henry Chaffee's book is something like 400 pages long. 60 pages of it are on random effects. The rest is on fixed effects. They didn't even have a good conceptual definition of it until 1947. Like, they'd been using these things since 1905, Fisher had, and until 1947, when Eisenhardt's paper came out in Biometrica, they didn't know what random effects were. They didn't have a definition for them. So that's the context that this is in. By the way, that's why a large number of fields don't use random effects still, because economists were porting this stuff over in the 1950s when the definitions didn't make any sense, and then they closed the gate after. And so they weren't paying attention to what ecologists or what psychologists or what epidemiologists were doing. They just had the book and then stopped citing it and started citing economists. So we had a problem where the tower started to collapse because lots and lots of people started using these models. Lots of different fields started kind of porting them in. They started borrowing fixed and random effects models in a more difficult way. A lot of them started appropriating them without giving credit. You can't really say whether or not certain economists just reinvented the wheel versus like copying the wheel's math proofs and then not giving attribution. They had a tendency to do that. I've seen econometricians write the same paper in two fields and not cite themselves in either. So a lot of it was just outright theft. But it makes it very, very difficult to build on what other people are doing in other fields up until we had the internet. So we ended up with what is ostensibly a game of telephone. I'm going to take Henry Chaffee's book, I'm going to read it, I'm going to write a paper that uses it in agricultural economics. I'm not going to cite it, so no one else can like go back and look and see if I understood it properly. And so someone else is going to cite my paper. And then other people are going to start building and building and building, and you end up with terms that are mutating. Sometimes people just made stuff up. That is very common in this field. I still remember kind of having this realization when I was reading a couple of papers, and they just had fundamentally different interpretations of what a random effect was. And then I just realized it's because one of them just made up their own definition, which is a fairly common thing for people who are using applied stats when they don't know what they're doing. So the definitions mutated, then they started to proliferate across fields, within fields, over time. And you end up with fixed and random effects, meaning very different things to very different people. Because again, the original book was designed for experimental design. Fisher's book was literally designed for people who were working in industry to do experiments. Like, it wasn't even an academic textbook. Academic textbooks didn't exist. It was for applied researchers working in manufacturing. And then Chaffee's book was a stats book that kind of aggregated a bunch of research, but still related to experimental design. So when people started porting it in, but they were trying to do things for non-causal modeling, data generating process modeling, which is every other field that wasn't doing experiments at this time, they had to tweak the definitions for them to make logical sense. So fixed effects can be a type of model using only within group variability to estimate model parameters. By the way, we're going to go through a bunch of different definitions. Don't try to write them down. You'll have the slides. I will walk you through the ones that are relevant for use here, but just hang on. This is going to be a wild ride. So fixed effects can be about a model. They can be a model that's just using within group variability. So you rip the between group variability out. If you're talking about students in schools, then you rip out all of the between school effects, and you just talk about the within school differences. They can be variables that do not vary across groups. So the variables are fixed for the entire population. They can be coefficients on within group varying variables. So the coefficients on the models from the first definition. They can be dummy variables that are used to remove the group variability. So instead of the x's you care about, they're the dummy variables you use to rip all the between group effects out. This is a fun one because economists like simultaneously think it's both things. So they get very confused if you actually call them on it. Are there any economists in here, by the way? Yeah. Normally, I think to check, ICPSR, they don't show up unless they're undergrads. So I can make all the economist jokes that I want. But I realized, one, I haven't checked, and two, I'm being recorded. So this is going to be fun. So instead of fixed effects, now we can talk about random effects, where the real fun begins. Random effect can be a latent variable that's made up of the expectations, the expected values of group membership on Y. So in other words, if you ran a model of student test scores as the Y and just put the dummy variables for school in, you took the coefficients off of all of them, and you stuck them in a new variable, that's the random effect. That's one version of a random effect. You are creating a latent variable from a bunch of school dummy indicators. It can be any variable that's allowed to vary across groups within a model. That's helpful, right? It can be the variance around the model intercept when the intercept is allowed to vary across groups. So a random intercept. This one gets used a lot in multi-level modeling literature. It can be the variance around any variable that's allowed to vary across groups. So a random coefficient is also a subtype of random effects. It can be a class of models where you just let something vary across the groups. It can also be just a type of model that is basically evil. It causes endogeneity, it causes limited variable bias. You will burn in the fires of hell forever if you ever use it. This is one of the more popular economics definitions of what a random effect is. Then we get to mixed effects models, where it's a type of model that uses both random and fixed effects. That's clear, right? This was me teaching it to myself over years, thinking that I must be the stupidest person who ever accidentally got into grad school, because all of these definitions show up in empirical literature in different fields. And silly me, I didn't realize I should just be reading my own field. So if someone says a fixed or a random effect, they could mean any of this stuff. They could mean a variable, a coefficient, the variance around a coefficient. They could mean multiple variables, multiple coefficients, multiple variances around multiple coefficients. They could mean a specific model or just an entire class of models. And that's not even talking about Bayesian random effects, which we're also going to talk a little bit about because that's what I was asked to do for the lab. That's a whole new ballpark right there. So that's straightforward, right? Everyone gets that. Everyone's going to pass the test, right? No problems. It's basically everything but y can be a fixed or a random effect in some version of language. For our purposes, pay attention to the color coding here. A fixed effect is going to be things like an alpha or a beta, something that is common to the entire population or the entire population under study. In the formulas to come, they're always going to be blue. If it's fixed, it's blue. For our purposes, a random effect is going to be mu. It's going to be a latent variable. It's going to be something that varies across groups. If it's a group varying intercept, it's going to be a latent variable. If it's a group varying slope, it's a little bit more complicated. But we're basically just saying this is a thing where the beta coefficient is allowed to vary across groups, or where the intercept is allowed to vary across groups. Capital fixed and capital random effects models are different. If it's got capital FE or capital RE, that means a class of models from econometrics. A fixed effect model in econometrics is any model that uses fixed effects dummy variables. It's any model where you're ripping out the between group differences. A random effects model is any model where you are allowing the group differences to be expressed with some kind of error decomposition. You're putting the thing in a residual, basically. These things are complicated because they were built in isolated literatures that never talk to one another in any meaningful way, except for the econometricians who were like stealing from the biostat people and just not giving them credit. The biostat people did it too, so it's fine. So why should you care about all of this? Why should you care about any of this? Like, I'm giving you some very, very convoluted terms. I'm telling you that the underlying problems mean different things depending on the kind of model that you're doing, and I'm basically saying this is a nightmare to sort through on your own. Why should you actually care about it? Why is it worth the headache of really thinking about this stuff, really like fighting your way through the empirical literature? We've got a bunch of distinct but pretty interrelated problems. I used to say 4, but there are more than 4 now because I'm literally just thinking them up. They can cause some pretty serious problems. Cluster data can cause some pretty serious problems. So now we're talking about like what are the problems and how do you fix them, basically. So the first and easiest, the one that you've probably heard before, is clustering is going to mess with your standard errors. This is what random effects were originally designed to fix, back with Fisher and with Chaffee's book, where they talked about random effects as basically being a standard error correction, something akin to Hubert-White cluster robust standard errors, except they predate it by decades. It was just a way for you to get experimental designs to yield generalizable standard errors. That's the most simple, easiest problem, but it's also the one that is most closely associated with this because it's the one that's oldest. It's the one that was first understood. Yes? In theory, it is going to make the standard errors more accurate. It can actually increase the standard errors. Normally, it will increase the standard errors because the clustering itself is making it seem like there's less variability to begin with. So normally, it's going to go the opposite direction for what you want for your hypothesis test. It can actually go the opposite direction, though. If within the groups you've got negative correlation, it can actually shrink your standard errors. So it becomes a really complicated issue. In practice, like 99 times out of 100, it's just going to be a more conservative thing to do if you're hypothesis testing. But it can have weird effects, especially if you've got lots of random effects and they're interrelated with one another. But this is the basic one. But this is also something that is pretty easy to solve with like 50 different standard error formulas. You could do bootstrapping, you could do cluster robust standard errors, you could do jackknifing, you could do panel corrected standard errors. You can do lots and lots of stuff to solve this problem now. So random effects aren't really necessary for it, but they work. They work fine for standard error problems. And if you're doing a proper experiment, that's the only kind of correction you really need. The problem is most of us aren't doing experiments, and even when we are, their designs aren't impeccable, so they could still have problems leaking over from random assignment malfunctions, from just random error, from the place that you did the experiment having an effect. This leads us to something called cluster confounding. Cluster confounding is the idea that you've got the same kind of concept at multiple levels of analysis, but they can go in different directions. Has anyone ever heard of Simpson's paradox? Or the Berkeley admissions paradox? There was a study that was done out of Berkeley that showed that when they just look at kind of average admissions across graduate programs, there's severe bias. This was decades ago, but there was severe bias against women in admissions. But when you look at the individual programs, there wasn't. Why? Because there were a few programs that were very, very large that didn't have very many women applying, like engineering. And so you end up with this optical illusion where depending on the unit of analysis that you're looking, you see an effect and then it goes away. You see this sort of thing in a lot of ecological problems, where at one level of analysis, it appears that the effect of X on Y is positive, and then when you zoom down, it's negative. When you look at individual schools compared to schools on average, you can see completely different directional effects. Different fields have different names for this. This is called endogeneity, or one of the definitions of endogeneity in econometrics. Lisa Hoffman, who's a psychometrician that I really like, she calls it squishing, because it squishes together the beta coefficients for the aggregate effect and the individual level effect. So if you're trying to talk about something like what is the effect of gender in a classroom, your individual gender, and what is the effect of the gender ratio in the classroom, if you don't put the gender ratio in the classroom, the two effects get squished together. They get confounded so that your individual level effect of your gender is trying to simultaneously, the beta coefficient is trying to simultaneously express the aggregate effect of composition and the individual level effect. It's trying to simultaneously say, this is the effect of my gender and also of being the only person of my gender in this classroom. Or this is the effect of my gender and being completely in the majority in this classroom. And you end up with lots and lots of things that this can affect. There's a fairly easy and trivial way to solve it, and that is just putting the cluster averages in the model and then deviating around them. This is what panel data econometrics models do implicitly. This is what most people in psych methods or in educational research do. This is something that stats people do, that like everyone does basically, but they don't talk about it in this way. So it's not always clear why they're doing it. Psychologists are really bad about that, by the way. They've been doing this for so long, but they didn't realize why. So they just think it's about interpretability. And they can't even recognize that if you don't do it, it leads to massive problems of inference that are incredibly concerning to entire fields of research outside of their own. So then we can end up with the really, really creepy stuff that doesn't get talked about a lot. You can have spatial diffusion across groups, where it depends on the physical location of the groups in question. If you're talking about doing a model of individuals nested within counties in the United States, which is something that's very common in political science and sociology, counties are next to one another. The borders are poorly designed and porous between them, so you can have effects spill over. If there's a natural disaster in the county next door to you, it's going to bleed over into yours and affect people living within that. If you're living in two states that are next door, if you're living in two countries that are next door to one another, and country A gets involved in a civil war, it's going to impact country B, because at the very least, country B is going to see some refugees showing up. So you get this spillover effect that was never talked about by Fisher because it was nonsensical in an experimental design. It was never talked about by Henry Chaffee because it was nonsensical in an experimental design, but it is incredibly important to understanding a whole range of questions out of political science, sociology, economics, ecology, pretty much anything that studies the natural world. Then you can have network effects across groups, so not just physical distance, but interactions across groups. We see this in political science where governors talk to one another. They actually have meetings. There's a National Republican Governors Association meeting, National Democratic Governors Association meeting. They get together and they talk to one another. They have each other's phone numbers and they plot advancing national policies in their states. They coordinate across implementation. They coordinate all kinds of things. Hospitals pay attention to one another. They read the same journals, they go to doctors go to the same conferences, academics go to the same conferences. So you have network effects that aren't just about space. They're not just about the physical placement of the groups, but they're about interactions between parts of the groups. This stuff was not supposed to happen in experimental designs, but this one actually does. If you're a psychologist and you've been doing experiments on Psych 101 students, I hate to break it to you, some of them are roommates and they're taking the class at the same time. And maybe they've talked about your experiment that is such a drag and such a waste of an afternoon. And so some of them actually know what the punchline is that you've revealed at the end. You get network effects like this all the time that never get talked about because crops don't talk to one another, right? This batch of beer that was being produced in one of R.A. Fisher's ANOVAs is not secretly colluding with the other batches to try and like mess up your inferences the way that people do. Then you can get temporal diffusion across groups. When we try to model time as the grouping variable, the fact of the matter is I am pretty closely related to what I was yesterday. And so if you're using days as a measurement indication, they're going to be aligned through time, and you have to model that appropriately. You have to be able to say, like, no, whatever was about me yesterday is bleeding into today's measurement and makes it different from 2 months from now, or makes it different from 10 years from now. Me, 10 years ago, I hate to break it to you, I was not able to give this particular talk. I was pretty able to give it yesterday. Pretty able to give it 6 months ago. I've changed it a lot since I did it last year. So you need to be able to factor that in. You need to be able to understand that the measurement occasions are correlated through time as they can be correlated through space, as they can be correlated through networks. If that's the kind of data that you've got, which is really common if you're doing data generating process modeling, then you need to think very critically about that. If you're doing causal inference, you get to just chop this stuff out. You get to say county fixed effects. I want to control for the fact that two counties are next to one another. I want to rip it out. That's what spatial econometrics does. It takes the spatial correlations between counties or between schools or whatever, and it rips it out of the data so that you only have to talk about the specific mechanism and not how it varies across different places. You can also have selection effects. This is a new and wonderful thing for me. You can actually end up with, because of the grouping structure, because certain people in certain groups are more likely to not show up in your sample. So for instance, if what you're talking about is something like, do people show up to take their math tests? So if you're studying math scores, truancy is a problem for math scores because you're going to end up with higher scores because presumably the people who are ditching would not have done all that well. And the people who are ditching are more likely to be at the same school to one another. You're going to have schools with high levels of truancy, schools with low levels of truancy. So the grouping mechanism itself is related to selection into the test score bank. It's related to the sample that you're talking about. You can end up with the exact same logic if you redetermine something like age group as the grouping mechanism in a survey. Younger people are less likely to respond to people who are doing a national survey. If someone's trying to figure out whether or not you're going to show up and vote for the midterms, young people are less likely to respond. Why? Because I don't answer my phone if it's not a number that's in my contacts because it's probably spam. Old people are much more likely to respond. They're also much more likely to have even still landlines where they can get a direct contact. So if you nest individuals within age or age group or age cohort or whatever you want, the selection effect is mirrored in the age group and not just at the individual level. So this stuff gets complicated really quickly. You can also have missing levels. This is a fun one that no one ever talks about. Let's say that we've got students in classrooms and schools. And we want to understand the effect of race on test scores. You've got students' individual race. You've got racial composition within the classroom. Now let's say a third of the principals are raving racists and are actively instituting punishment policies that prevent black people from doing well, prevent any kind of minority from doing well, prevent immigrants from doing well. That's not an individual level effect. It's a school level effect. It's not going to be dealt with by any classroom level characteristic because the teacher's not doing it, at least not directly. It's a school level effect, but it actually proliferates down because every classroom is going to show the same effect by virtue of being in that school. It's going to affect all the classes in there, but you can't solve it directly by looking at the classroom effect. So you end up with this weird emitted variable bias problem that's causing what looks like cluster confounding. It's causing what is in fact cluster confounding, but you can't solve it because you're not looking at the right levels of analysis. All of these are special cases of emitted variable bias. Some of them just are not relevant to what you do, right? Some of them are just never going to happen with the kind of data that you're working with. Some of them might, and you've never thought about it. Some of them might, and it's actually a pretty easy fix. Students in classrooms and schools is a pretty easy fix because you've got a pretty well-defined data set there. What happens if there's a cross-classification? What happens if it's not students in classrooms and schools? What happens if it's students in classrooms and schools? And there's a neighborhood effect where some people in the school live in a really bad neighborhood, some people in the school live in a really good neighborhood, and believe it or not, like, your mother fearing that you're going to be shot walking to school probably has an effect on your educational ability or your educational attainment. How is that going to impact this? Well, it's complicated, it's hard. This is all hard stuff. But the Most basic thing is just to look at the question that you're asking and try to figure out the implicit structure. Try to figure out where all of this stuff can come in. In what ways are we deviating from what Fisher and what Henry Scheffé were talking about when they were talking about random effects and fixed effects? All of these are special cases of what economists like to call endogeneity. A lot of times when someone says endogeneity, they mean joint causation, reciprocal causation, X causes Y and Y causes X. What it really means is there's something in your error term that is moderating the effect of X on Y. It could be past values of Y. It could be past values of X. It could be levels up higher versions of X. So instead of your gender, it's the gender ratio in the class. It could be higher than that, and it could be a policy-specific effect. It could be spillover effects across groups that are correlated with one another. But it's something that is left in your error term, it's sucked in, and it is giving you a misrepresentation of what your mechanisms look like. This isn't really that big of a problem in practice if you're doing predictive modeling, because we don't care about the mechanisms. This only affects our mechanisms. But it does matter because the structure is much easier to model if you actually model with variables instead of putting random intercepts and random slopes on everything, and instead of allowing correlations across the groups for everything. That's a fragile model that's going to break the software 9 times out of 10 if you really lard it up with everything. So even in the best case scenario of you just not caring if you get the beta coefficients right, it's going to make your life easier if you try to work on this stuff theoretically first and try to figure out a model that makes logical sense. In general, what we're talking about, though, is just the effect of X on Y is inconsistent across groups. That's all random effects endogeneity means. Put the groups in versus taking the groups out, and the beta coefficient on X changes. It's bouncing around depending on how you do it. This is actually the basis for one of the more famous tests for this problem called a Hausman test, where you run a model where you account for the group structure using dummy variables, you rip it out, you run a model where you don't, and you compare the beta coefficients. And if they're bouncing around based on a chi-square test, then you've got one of these kinds of problems. And you should do something about that, please. Economists then say, just put the dummy variables in, which is not really satisfying, but it's at least something. You can do a similar kind of thing with likelihood ratio tests and model comparison tests, where you see what happens to the model fit when you try to put some structure in the model. Does it improve the model fit with a likelihood ratio test or with a Bayes factor, or with any of the model comparison tests like that based on information criteria, if you put a random intercept in or a random slope in? But all of this is about trying to explain away the differences in X on Y with some kind of structure, with an interaction, with spatial diffusion, with network diffusion, something. Does that make sense? I know we're hitting a lot here, and it's going very fast. Has anyone ever been exposed to this stuff before in your I know you have, I taught it to you. Has anyone ever been exposed to this stuff before? A little bit? It's a weird thing to think about, but this is the entire reason why the books seem to contradict one another, why the papers seem to contradict one another, because they're talking about it in different contexts, with different kinds of data. If you were only ever doing experimental designs that are based on like plots of crops, if you're only ever testing fertilizer on corn, it's never in a billion years going to occur to you that there could be network effects where the corn is talking to itself across the plots and they're coordinating or something. Like, that's just not logical, but it is logical for people unless you keep them segregated. It is logical for spillover effects to happen across countries because that's how borders work. So what does this mean in practice? Here's the part where you're going to start wanting to cry. I'm sorry. I'm not sorry. Your standard errors are probably wrong. That's the easiest one. That's the one that we've known since Fisher. That's the whole early reason they thought random effects were a good idea. Your coefficients are probably wrong too, because of that cluster confounding thing, because of higher levels that can moderate lower level effects, because of diffusion across groups. You probably don't have the right variables in your model in the first place, because again, that whole cluster confounding thing, like maybe you just didn't think to put the gender ratio in your model or racial composition in your model. And because of that, you don't have the right variables. You're probably not really even testing the hypotheses you think you're testing. This happens a lot when people start shoving fixed effects dummy variables, capital F, capital E, like economists do, into models left, right, and center, and they say, I'm going to have state level, US state level fixed effects dummy variables. So I'm going to shove 49 dummy variables into my model for states, and then I'm going to shove 39 dummy variables into my model for years, for 40 years, and then I'm going to report the results. And I hate to break it to you, but the results are wrong because that model specification makes no sense. But they do it anyway, and there are lots of things that are based on it. Hypotheses don't correlate with the analyses in a lot of cases. And this is not, like, I talk about economists because I was trained by an econometrician, so I'm more familiar with what they do and what political scientists do. But I have not seen a field yet that was immune to this sort of problem. Oh, also, if you try to predict fitted values, if you try to predict probabilities or propensity scores, model's probably wrong, and your values are definitely wrong. If you're trying to do propensity score matching or predicted probabilities to include in a model, or you're trying to do machine learning and you haven't incorporated the structure that's inherent in your data, you're getting things that are on average right and wrong for any individual case. And you're more likely to get more accurate predictions if you actually take into account group-specific deviations from typical. They're just biased. They're wrong. Any questions? We're having fun, right? You all wanted to come here. Okay, so we've talked about the underlying problem. The underlying problem is a fairly severe one. I'm trying to see what time it is. I think it's 3 o'clock. Okay, we're right on time. How do we actually deal with this in an appropriate way? I've given you a little bit of a hint on this when I've talked about group mean centering. There's a bag of tricks that you can do to kind of pare away at the different problems. This is not something that I have ever seen written down. I'm working on some papers that try to articulate kind of a general approach to this problem. But how do you actually kill this beast? How do you really think about cutting off the individual heads in a coherent, systematic way so that, one, you're just not wasting a bunch of your time, and two, you're not missing something like selection effects cropping in test scores and that being clustered with schools. And maybe, I don't know, if you have a school where you know people do particularly badly on tests, they get some subtle encouragement not to show up on test day so that the principal's test scores don't look terrible. How do you deal with things like that where you probably didn't even think about it? Because selection effects and missing data problems really come into play here as well, and we never actually think about them. There's a little bit of literature, mostly in psychometrics, that tries to deal with these things in a reasonable, logical way, but it's been ignored by most other fields. So how do you actually do this? You have different solutions for different problems, right? We've been talking about an array of different problems, and the easiest thing is just to tackle them one at a time, systematically, to think about, do I have this problem? Do I potentially have the standard error problem? Do I potentially have the cluster confounding problem? Do I potentially have selection effects problems? Or network diffusion problems across groups? Or spatial diffusion problems? Or temporal diffusion problems across groups? If you don't have temporal data, if you don't have multiple measurements over time, you can't have temporal diffusion across time in your grouping structure. So we can already dismiss that one. You don't have to test it if you don't have it. If there's no way that your grouping structure can talk to itself, can talk across groups, it's going to be really hard for you to have network effects. But this could be really subtle and not something that you've got represented in your data, right? Who in here has really thought about the fact that hospital administrators go to conferences with one another and talk about how to, write their IRS 990 forms in such a way that they get to expense more money on uninsured patients? Like, until I started working with that data, it never would have occurred to me that hospitals are talking to one another ostensibly because they're it's supposed to be in competition with one another. But no, they talk to one another, they read journals that other people write in, they have conferences, the same as academics. So you end up in really weird situations sometimes, but at the very least you can think very critically about the data that you've got and try to be as aggressive. Pretend that you're trying to make the argument that your data have a particular structure that you don't want. Imagine that this person is the nastiest reviewer you have ever come across, and they are trying to make the point that you have left out some important structure in your data that could bias your results. Make as good faith of an effort as you possibly can to argue why this thing that is inconvenient for you might be there. And if you can't make a claim that's at least plausible, then you ignore that particular one and focus on the others. So standard errors are the first one that we've talked about before. Again, they're the super easiest one to fix. There are 40 trillion different standard error formulas that you can use. They're not going to suffer from the same kinds of correlation problems that just assuming conditionally independent errors will. Random effects are one of them, and they work very well, and they're actually really easy to implement, but you could also use cluster robust standard errors, assuming asymptotics are right. You could use bootstrapping or jackknifing non-parametric formulas, all kinds of things. So this is the one that people are going to come back at you most often because it's the one that's most widely understood, but it's also the one that's just super easy to fix. I already talked about that. Endogeneity itself, something being left out of your model, sucked into your error term that is important and related to both an X and Y in some way, or at least correlated to an X and a Y. That's a more problematic issue. That's the one that we really have to think very critically about and pare down into bits and pieces. So you've got three different approaches. You can hack out the affected parts. This is what economists are usually going to do, just on principle. But if you're doing causal inference modeling, this is what you should be doing, regardless. If you're only focused on a single mechanism, hack everything else out that could be interfering with it, that could be moderating it, and just look at the unmoderated mechanism. It may not ever exist out in the wild, but your first step in causal inference modeling is always just to try and get a sense of, does this thing, absent everything else, absent all context, as if we were doing an experiment, does this thing matter by itself, and what's the appropriate magnitude of the effect? And then you can layer on other things. You can do heterogeneous treatment effects models. You can make a more complicated, more complex assessment of the measure itself of the mechanism, and you can try to build onto that. But the baseline is going to be hack out the affected parts. This is something that for a long time kind of repulsed me because I couldn't think of why you would ever do this, because all I was trying to do was model the data generating process. All I was trying to do was understand in a regression framework. But it logically makes sense if what you're doing is causal inference. And you are wasting a truckload of time trying to model school-specific effects if they don't matter for the hypothesis that you're testing. If what you're trying to test is the direct effect of a student's individual level race on their test scores, you don't need to know that the principals in a third of the schools are racist scumbags. You just need to be able to control for the fact that there are school level differences by putting dummy variables in the model. If that's not the question you're interested in answering, then that's not the model you should try to use. Lots of people are interested in understanding just the direct effect of students' individual race, controlling for everything else. Other people want to say, okay, what is that effect in context? What is that effect when you don't rip out all of the other things in the model? You can just allow the effect of X on Y to vary and just get on with your life. You can just stop assuming context conditionality. This is what you're going to do with machine learning stuff. You're just going to say, beta coefficient here is allowed to vary across groups, or the intercept is allowed to vary across groups. This is a random intercept or a random slope model. It's the basis for modern multi-level modeling. You're not really differentiating between an individual's race and their classroom's racial composition. You're just saying, I think the beta coefficient can bounce around across classrooms or bounce around across schools and just get on with your life. You can't really answer very specific hypothesis tests about that, but you can still write hypothesis tests that are in line with that sort of thing, or you can do predictive modeling. You can just say, all I really care about is predicting Y, so I don't need to understand why the structure works the way that it does. All I need to do is acknowledge it. All I need to do is acknowledge that the beta coefficient jumps around a lot. And then you can just model the sources of endogeneity. You can build a proper model of the data generating process, and you can say, no, actually, there are individual level factors, there are school level factors, there are classroom level factors, all of these things interrelate. Maybe there are network effects, maybe there are church effects, maybe there are team sports effects. All of these things come in, and you try to get as good of a picture as you can with it still being relevant to what you're doing. And maybe you alternate back and forth between all three of them in different projects. So you have 6 basic equations where you can do this sort of thing. We're actually going to show the implementation of how to do these things in the lab later on. Like, they're more complicated to explain than they are to implement. Implementation at this point is super easy. But you've got 6 basic options to deal with. The first one is a classical regression model. And in this case, remember what I said about the color coding. If it's blue, it's a fixed effect. That means it's a constant effect. We're not assuming it varies across groups at all. We're just saying the average effect of X on Y is good enough for everyone, irrespective of the school that you're in, irrespective of the hospital that you're in, the state, the country, the time period, whatever. What about this one? Anyone familiar with this? Economists are going to call this a fixed effects model. These are group specific. You can't see the little thing. I don't know why it's not. It shows up there. That's helpful, right? The J's right here are just group specific dummy variables. They could be dummy variables for people if you were doing this in a psych model, though people are going to look at you like you're nuts. Statisticians are just going to call this weirdly inefficient because you can just do a multi-level model. Again, psychologists, this is the expression of the guy that I used to TA for when I told him economists did this. Because he is a psychologist. And every single psychologist you ever talk to is going to give you that exact expression when you explain to people, or when you explain to them that they're putting dummy variables in for people.
You should talk to more psychologists.
Yes?
So, I'm in psychology, and I'm making that face. I don't know if it's for the same reason, but I just keep thinking, like, everything I've ever been taught always told me you want to put as few variables as possible, because at least I deal with kids, we usually don't have big populations.
Yeah.
And so, if you have 20 variables, then...
So this is another, the question for the people who couldn't hear because she's not mic'd. One of the problems that you run into is there's pressure against doing what I'm suggesting because of degrees of freedom issues. You don't have a whole lot of groups, or you don't have a whole lot of people within groups, and therefore you're really constrained on the kinds of models that you can run because of this. This is one of the reasons why people just tend to specify, just allow things to vary across groups instead of trying to model it with covariance. You just don't have a lot of room to maneuver. I've thankfully in my work not had to deal with that because I've got data sets with hundreds of groups in them and tens of thousands of observations. But other people, especially a lot in psychology or education and in panel data econometrics, end up with these degrees of freedom problems. And if that's the case, then you have to get really, really creative about verifying, is it okay to leave a variable out? Is it okay not to have this cluster-specific variable like gender ratio or racial composition in your model? And one of the ways that you can do to test that is a Heckman or a Hausman test, where you just say, what happens if you control for the group structure with dummy variables? What happens if you don't? Does it really bias all of your effects, or does it just bias two? Right? So if you run a model and you rip out all the between classroom variability in the students in classrooms model, you're trying to model test scores, and you've got 5 different variables about individual student characteristics, and only one of them changes. It's only race. Then that indicates that the others aren't affected by cluster level effects, and you can just leave them out. Maybe you can't test your hypothesis that way because you've also got that consideration. But in general, like you kind of have to be much more systematic about paring things down. There are other fields, by the way. Psycholinguistics, anyone in psycholinguistics in here? Those people are nuts. They want you to put random effects on everything. Every single parameter in your model gets a random effect. It doesn't matter if it improves model fit. It doesn't matter if it improves anything in the model. It doesn't matter that you can't do it in most software packages. They say, well, just become a Bayesian then, because you have to do it. This is something, I'm not even exaggerating a little bit. I've gotten into heated arguments with people who say it doesn't matter if it's statistically significant, you should put it in, because they're basing this off of random effects are useful from Henry Chaffee's language, and they're doing lots of experiments. So it makes the standard error correction better. And so maybe they want, I read one paper, and I actually had a student who was doing psycholinguistic stuff, where he came to me and he showed me a paper that had 14,000 random effects in it. I hate to break it to you, that's not going to work in most software, and also you have degrees of freedom problems, quite a few of them, but they want it in their literature. So you end up pulled in both directions sometimes, and you have to know your literature, you have to know what your reviewers are going to want, and you also have to kind of be able to live with yourself about doing a model that you know is garbage. But yeah, so fixed effects. This is one that's just inherently problematic if you've got degrees of freedom problems. If you don't have a whole lot of groups, it's not an issue. Like, anyone who does survey research puts gender or race in the model, because there's, in the survey at least, there's only 2 classifications for gender normally, unless it's something that was conducted specifically about gender. There's male and female, and then maybe did not respond. And then there's maybe 4 or 5 racial groups. So that's never really an issue for survey research. If you're talking about hospitals, and you've got 1 observation per hospital, you can't really do hospital level dummy variables. If you've got 2 observations per hospital, you can't do hospital level dummy variables and say anything else. So you really have to know the data that you've got and the restrictions that you've got. Okay, what about this one? The first one was an econometric fixed effects model with dummy variables. I'll give you a hint. We've only really talked about 2 models so far, fixed effects model and random effects model. It's a random effect. Random effects model. Economists are going to call anything with a random effects model. It's a class of models with this thing in it. What I usually use is mu. Statisticians and psychologists are going to call it a random intercept model, because the intercept, the alpha parameter, is going to vary across groups. It's pretty common. So you've got a fixed effect. These are the things that are common to the entire population. This is the part that's varying across groups. It's constant within groups. The random effect value itself just does not vary within a group because it's just the mean. It's the conditional expectation of y given a bunch of covariates. So if this was a students in classrooms model and you wanted test scores as y, no x's in the model mean it's just the classroom level test score, the average test score in the classroom. You put gender in, it's the average classroom expectation once you've ripped out the gender gap. So it's a pretty straightforward interpretation. Yes?
Can we go back to the last previous equation? So in here, then J.
J is a group. So it could be a hospital, it could be a person, it could be a country, anything that's the grouping mechanism.
And they're not ordered because you listed out here as.
They could be in any order, yeah.
But that's all of this group level variable that you're researching. You are using the same data, so they have similar effects all along as X.
So I am, people yell at me about this. In order to make the slides less busy, I am pretty light-handed with my subscripts. So don't assume just because there's no subscript that the beta coefficients are equivalent or anything like that. This is the beta coefficient for group 1. So it could be the high school that you went to, and group 2 could be the high school in the next town over. And there could be ordering. If the groups are years, then one of these groups is going to be 1984, one of these groups is going to be 1985, and then there's implicit ordering between them, and you have to figure out how to deal with that, usually with a time trend or some kind of temporal spline or a polynomial for time. But you don't assume anything about the group structure by specifying something like this. All we're doing here is saying, here's a dummy variable. I want to rip the effect of this group out of this. These X's are the things that we care about. These are the things that we are ignoring. In most output, the software doesn't actually even report these if you're doing a fixed effects model, an econometric fixed effects model. This one is literally just taking the beta coefficients off of all the J's and stacking them into a single latent variable. And that latent variable is mu sub J. So instead of 50 parameters or 500 parameters, you now have one parameter. You can call it a variance component. That's what lots of people call it. You can call it a latent variable. You can call it a random effect. You can call it a random intercept. The problem is this could still be related to the X's. You're not ripping it out directly with a bunch of dummy variables. You are leaving it in and just including the expectations. So it works as a standard error correction. That's all it really does. But it gives you a lot of leverage to be able to see if you've got other problems. Yes?
In this case, you could conclude like, okay, this is the effect I see in X on Y after accounting for the baseline, right?
In this one, no. In this, all you can really tell is this is the effect of X on Y, and assuming it were like an experimental design, this is the appropriate effect. If any of those problems that we talked about, other than the standard error correction problem, are present, then the beta coefficients for X could be wrong. So then you have to go and systematically test that, and it's fairly easy to test because you compare this model to the model in the previous slide with the dummy variables in it, and if the beta coefficients on the X's you care about are different, according to some kind of test, usually a chi-square test, if they're different, then you know that there's a problem with this model and you have to move on to something else. That's a Hausman test. You can do back-ended versions of that with likelihood ratio tests, which we're going to show in the lab. Like, there's lots of ways to evaluate this, but essentially what you're saying is there's something still important. It's buried within here. It's buried within my mu sub J, and it's related to one of the X's I actually care about. It's related to student level, race, or gender, or income, or anything like that. And so I need to pull it out of this. You can think of this as a trash can. You can think of this as a holding vessel. You have to pull out the stuff that you actually want to keep, because this model right here is assuming it's noise. It's assuming the same thing that it would assume if it were still subsumed into the individual level error term. Any other questions about that? If it's not quite clicking yet, we're going to go through these equations again in a minute when we contrast it to Bayesian models. The nice thing is the multi-level, the structure part stays the same. The interpretation of the coefficients changes quite a bit. Anyone in here done Bayesian stuff before? A couple of you? It's a wild time. Okay, so this model, anyone want to tell me what this one is? Economists are going to call this a Mundlach device because Yair Mundlach in 1978 wrote a paper showing how to do this as a way to correct for cluster confounding. He didn't call it cluster confounding, he called it endogeneity, but it's essentially a problem where mu is still holding something that we care about. In this case, it's holding some kind of classroom level characteristic if we're doing students in classrooms. So the student level or the classroom racial composition or gender ratio or something like that. So in this model, we just include the group average for all of our individual student variables, or the hospital level average for all of the individual day measurements. And we take deviations from that. Economists are also going to call it correlated random effects. Statisticians and psychologists call it group mean centering. Psychologists tend to do this kind of on its own because it makes things interpretable if you're accepting that they're going to be person-specific and like observation-specific effects. But it also has the nice knock-on benefit that it avoids you making a model misspecification error that can give you very wrong answers. So again, we've got fixed effects in the model, we've got random effects in the model. This is a group-specific effect. Right, this beta right here, the beta x bar j. That just means it's something that doesn't vary within groups, it varies across groups. So the gender ratio across classes can't vary within classes, right? If half the students are male and half the students are female, then every single student in that classroom gets a 0.5, or however you're coding it, for the gender ratio. So it's a level 2 effect. And by including that as a variable and pulling it out of this, we can decompose these. We can pull them apart so that the clusters are no longer confounded with the individual level effects. Or in the language of Lisa Hoffman, they're no longer squished together. This is the first step that you're ever going to want to go to if you're running a model and you can tell that this is wrong. If you can tell by using the dummy variable trick, by using a Houseman test or likelihood ratio test or whatever, that there's something left over in this mu sub j that is correlated with an x, the first thing you do is start doing Mundlach devices group mean centering. Economists will also call this a Houseman-Taylor model because Jerry Houseman, the guy who invented the Houseman test for this specific problem, also wrote a paper showing how to do this specifically in Econometrica in 1981. So this is something that is recognized as a valid approach in every single one of the fields that I've talked about so far. This is the easiest, most straightforward thing to do, especially if you are constrained on degrees of freedom and you don't want to use a bunch of dummy variables. So then you've got something like this. What happens if it's not just cluster confounding? We've also talked about higher levels of effects where it could be a principal problem. It could be that the principals in a third of the schools are racist. That's not going to be solved by this model. It could be that there are school level spatial effects so that two schools that are next to one another in similar region are affected by the same kinds of things like poverty. It could be that there are network connections where people within the groups are talking across groups because there's a conference or something. And so none of that's going to be fixed by this. So there are a few ways that you can go about solving that kind of problem, but you need to test for them. One, by just figuring out what the structure of the correlation would be. If there's spatial correlation across groups, you need to build a spatial matrix and say, like, these groups are correlated. If it's across time, you need to say, hey, I think 1984 is more closely related to 1985 than it is 2016. And so you need to do something to impose that structure that you can understand logically about your data. No one outside your field can tell you what that's going to be because that's really domain specific, other than temporal data because everyone understands how time works, right? Presumably none of you are working with data on like fortune tellers where the effect precedes the cause. So we can start on something like this. The most straightforward approach, it's called a random coefficients model. also a varying coefficients model or a random slopes model. And in this case, what you're doing is you're saying, I've got, usually you're going to specify this with group mean centering as well, and you're going to say, like, okay, let's rip out the cluster confounding parts, let's model them properly. If there's stuff left over where this beta coefficient right here, I keep using this and it doesn't work on these screens. This beta coefficient right here is still bouncing around across groups. If it's still bouncing around across groups, the next thing you can do is just say, okay, just let it, right? Just let this be a variance around the groups. You stop assuming context conditionality, group conditionality holds, and that the beta coefficient is the same across all the groups, and you just say, it follows a distribution here, let it, and move on with our lives. This may not answer all the questions that you want, but it's a pretty good kind of intermediate step between moving forward. And it's a nice little trick because it, if you run this on a bunch of models and do model comparison tests in a very specific way, which I'm going to show you in the script, you can actually help figure out whether or not your X's are going to be affected by this other stuff in your model. That could be network correlations, it could be temporal correlations. Any of this stuff, it's a fairly easy way to pare down the potential problems that you've got to deal with and do the simplest model that you can that's still not assuming anything terrible, right? And by the way, this mu sub j right here that's attached to xij minus x bar j, that is literally just the beta coefficients by group, recentered around the grand mean beta coefficient, recentered around the model's coefficient. So you get this distribution of an effect. Yes?
So when you add this, as a random effect, and you let it vary, why do you also keep it as a fixed effect?
Because it needs some, so the question was, when you add this in as a random effect, why do you also add it in as a fixed effect? Because these two things are interacted with one another, and this acts, the beta coefficient and so the alpha for the random intercept acts as the center. So you recenter it around that so that it's directly interpretable. Has anyone worked with interaction terms where you've been told to recenter the interactions at their means so that you can interpret the constituent effects? It's the same logic. You're just trying to recenter these so that they're giving you reasonable values, and you're not just starting at the kind of origin. So it's the same reason why you have an alpha in most statistical models instead of just suppressing it and having it run through the origin, because the intercept makes things more interpretable. And it's the same underlying logic for a group varying slope, a random slope, is you would like it to be centered around your beta coefficient, because then you can say, well, this is the effect of student level race on their test scores. And in this school over here, the effect is a standard deviation below what it is on average. This effect is a standard deviation above, or this effect is a letter grade below or a letter grade above. This school is doing particularly bad, this school is doing particularly well. If you care about interpreting the schools, if you care about thinking about it in any way other than as like an error component that you just kind of think of as a cloud of horribleness, then recentering these things around the fixed effects is a good idea. Any other questions about that? Okay. So now we got this one. Anyone want to wager a guess what this one is? I got lazy about coloring these in because there's so many of them. Basically, this is the most fully parameterized version of the model that I've been talking to you about. This is the nightmare scenario where you've got every single possible kind of endogeneity problem. So we've got to include d-mean, like group means for the clusters, and we've also got to d-mean them. Then we've got to include the group intercepts. Then we've got to include random coefficients on each of them. Then this one is the network lag, NJ, meaning the groups have a varying effect so that groups that talk to one another, there's spillover effects. So you can have that, then you can have the network interaction, so that the effect of, like, I don't know, race or something is moderated by the groups that you're next to because there are spillover effects. Then you can have space, and it does the same basic thing. Then you can have time, and it does the same basic thing. Then you can have Z, which is basically anything else that you can think of. It might be a selection effect. This is the horror scenario here. So I'll give you an example of what this could be from my dissertation work. My dissertation was looking at attitudes towards same-sex marriage and how differing levels of homophobia in the political environment can affect not just your base rate of support for things like same-sex marriage, but how your personal characteristics affect your policy positions. So in general, more educated people are more supportive of minority rights. That goes for gay rights. Less conservative people, more liberal people, also more supportive of gay rights. Less religious people, more supportive of gay rights. This is in general how it works in the survey data. So we're talking about the specific mechanisms, right? This has been, validated in experimental designs. This has been validated with data generating process models. It's pretty consistent. Unless you change the context that you're in and go to 1984, in which case education no longer predicts attitudes towards gay rights, religious affiliation doesn't predict attitudes towards gay rights, political party doesn't predict attitudes towards gay rights, race, gender, age, nothing. Nothing in your model is going to predict attitudes towards gay rights because almost everyone in the United States in 1984 was anti-gay rights. There's no variation in why. So there's nothing for the mechanisms to actually act upon. They're all being suppressed. They're being moderated by the context. So then we take a survey and we measure this, 1984, then 1988, then 1992, 1996. We keep measuring this, and all of a sudden, all of these different mechanisms that individuals have start to help you differentiate attitudes on gay rights. They start opening up, and the magnitude of the effects gets bigger and bigger and bigger. And by 2008, knowing your political party in the United States is heavily predictive of attitudes towards same-sex marriage. Knowing your religious affiliation is heavily predictive. Knowing your education is heavily predictive. This is what I mean when I say the beta coefficients are jumping around across the grouping mechanism. The beta coefficients in question, your beta coefficient, your effect of your education on your attitudes towards gay rights was 0 in 1984, and by 2016, it was large and positive. Is this a problem? It depends on the kind of question you're answering. If you put dummy variables for year in the model, you're going to get nonsense because it's going to tell you, on average, what the effect was in 1996. If that's not the question you want to answer, then you need to do it with a multi-level model, and you need to account for the fact that 1984 was more like 1988 than it was 2008. And you do that with this component right here, this T sub j, time sub j. You put time in the model as a variable. You can put it in as a linear predictor. You can put it in quadratically if you think that the effect deteriorates over time. And then you put it in as an interaction, and you say, I think it's not just an intercept difference. I think that gay people didn't just become more popular. I think that it's directly affecting education and race and gender and party ID. All of these things for all of the different, for time, for space, for networks, for sample selection problems, all of these things can have that same kind of pattern. And so ostensibly the worst case scenario, well, I say worst case scenario, the most nightmarish case scenario for you to model and the best publication you're ever going to get is the one that actually models all of these things simultaneously. But ideally, you would not want to do that at once. You would want to pare them down and say, time can't be a factor in this because I don't have temporal data, I have cross-sectional data. Or if time could be a factor, you want to actually look at it. Look at the version that has dummy variables in it for year. Look at the version that doesn't, and see if any of your beta coefficients are jumping around. And if they're not, then you can reasonably assume that you can leave time and the temporal interactions out. You can do the same with space, the same with networks, the same with any other level 2 characteristic, level 3 characteristic, level 10 characteristic. It's about you thinking about it in a systematic way and trying to make less work for yourself in a logical way. You do not want to start with this model. If you try to start with this model, it will not run. The software will not work for you. Even Stan, BRMS is a wrapper for Stan, by the way. Like, that's going to take like 6 months of work to get the priors right, to get the thing working properly with no degeneracies in the model. Like, this is not a pleasant experience to start with, so you should probably start with something simpler. Or at the very least, make sure that if you have to include networks or space or time or Z, anything like that, that it actually matters ahead of time. And you can test that without running the full model, just with the Houseman test, just with the dummy variable comparisons, or with likelihood ratio tests. You put time in the model and save the results, take time out of the model, save the results, compare the two things with a likelihood ratio test or with an AIC or BIC or something like that. And if it improves model fit, then you should probably have it in the model. Does that make sense? Yes.
In here, you talk about all these different, mathematically, I don't know if the mathematician but they seem to be calculated or in the model in a similar way. Like, I don't know. I'm not
So
sure time.
This is a very, very good point. So for the people who couldn't hear, she was remarking on the idea that mathematically these things are entering the equation in a very similar way. They're interchangeable with one another. You're talking about group correlations for most of this. Are the groups independent? It's called an exchangeability violation in the technical literature. Are the groups exchangeable so that if you pulled some of the groups out and randomly drew some others and put them in, is it going to make a difference? For years, yes, it will. If you randomly take out 1984 and pluck in another year and put it in there, and you get 2047, it's going to make a difference. The groups are not exchangeable with one another. They're not even conditionally exchangeable with one another. That makes a conceptual difference. It makes a statistical difference. But the fact that I've got them broken out apart by time, by space, by networks is not a mathematical distinction. It's a theoretical one. It's one that's designed to help you get a handle on all of the different practical ways that your data could be inexchangeable, that your data could be violating this exchangeability assumption, that your data are not as if like experimental designs. So in practice, this is a useful framework for me, and I've been combing a lot of different bodies of literature to try to come up with, like, these are common things. Like diffusion literature, like, passes lots and lots of different distinct bodies of literature where you can have like a thing in this group or a thing in this person diffuses out and affects other people. Network research does it all the time, but you can have, if you've ever done survival models or you've ever done event history models, like lots and lots of diffusion processes happen. So I'm trying to identify things that are common that you can kind of carve away at the things that are sucked in this trash can, that are sucked into this group specific error term, and meaningfully pull them out so that you just don't get left with something that is still in there, that is still important, but you just don't conceptually know what it is. Some of them may just never come up for you. Some of them may be completely unrelated to the kinds of things that you're studying. Others can be very problematic. Does that make sense? Okay, now we do Bayes. Someone tell me what time it is? 3:45, okay. We're gonna go through Bayes. We're not gonna make it through the whole slide deck. I didn't think that we would, but the back end of the slides are relatively straightforward because they're me reversing the structure of this talk and giving you, if you've got a specific goal in mind, what kinds of models you use, and not what kinds of models do what kinds of things. So it's the inverse of the presentation previously, and it's much more straightforward for you to follow. So you'll be able to get that, and it makes much more logical sense. So we start, if we're going through Bayes, with this kind of equation again. Does anyone remember what this is? Linear regression, right? I may have fried your brains by now, but at least you recognize a regression. It's just a classical linear regression model, fixed effects model. That means these point estimates, the alpha and the beta, the intercept and the slope, are common across everyone. We're not assuming that they vary across groups. Now, if we want to turn this into a Bayesian model, what do? This is where I'm really glad that there aren't Bayesians in the room, because a real Bayesian would scream at me. From a mathematical standpoint, you just do that. You just say this is the Bayesian model. That's all. It's the same syntax in the software. Like, not a whole lot changes from a practical standpoint. They're usually going to interpret, like, they're going to get a beta coefficient and they're going to get an intercept, and they're going to like interpret it the way that most people interpret maximum likelihood estimates. That's mostly because people interpret maximum likelihood estimates wrong. The way that you've naturally been inclined to interpret them is the way that a Bayesian would interpret their results normally. In practice, this may be the results that you report in the table, but what you're going to get is this. You're going to get theta density. So instead of a point, instead of a specific number for the effect of x on y, you're going to get a distribution of the effect of x on y. Instead of a specific number for the intercept, the model intercept, the alpha, you're going to get a distribution among the entire population. You can think of these as partial derivatives across the entire population if you want. But this is the practical difference from a mathematical standpoint between Bayes and maximum likelihood. Notice I'm kind of waving my hands away at priors right now. Priors are things that you do to your beta coefficients or your intercepts or anything else that you're estimating in the model to modify them in some way. You can think of them as weights. I don't really have enough time to go into them because I have a whole lecture just on priors. So we're kind of hand waving a little bit, and you get to, if you ever run into an actual Bayesian, you get to tell them how terrible I was because I didn't do good enough justice to priors. But for all intents and purposes, you can think of maximum likelihood as a special case of Bayes. It's a case of Bayes that has flat priors on everything so that you're not putting weight on anything. You're just letting the model specify the distribution that it wants. So, and this will become much clearer when I actually introduce the software, because the syntax is almost identical for maximum likelihood multi-level models versus Bayesian multi-level models. So then we go back to our random intercept model, random effects model, random intercept model, random intercept model, according to economists, statisticians, and psychologists. We've already gone through this in some depth, so this should be ringing some bells. And we talk about this again as fixed effects. These are point estimates that are on average right for everyone. We're not saying they vary across groups at all. We're just saying this is the number that should apply to everyone. And then this is the latent variable. That's just the expectations for the intercept here. You took the dummy variables for the schools or the people or whatever, and you took their beta coefficients and stacked them into a single variable and stuck it in the model. You can do that a bunch of different ways, but it's all the same basic logic of you just taking those expectations and sticking them in the model, with the caveat that this actually ends up being shrunk a little bit. The outlier values get dragged towards the average. This is called Bayesian shrinkage or empirical Bayesian shrinkage. It's just a process that happens in this, but it also happens with priors in a Bayesian model. It happens a lot. You can think of it actually conceptually like regression to the mean, where the longer, as you put more data in a model, like outliers tend to get weighed down. Now, if we want to switch this, we have a Bayesian random effects model. No one's going to laugh about my abomination joke. You're just all tired. Basically, what this is doing is it's still saying, I don't think we have any variability across groups within our x's, but we still get a distribution, a density, instead of that point estimate. So instead of this being a maximum likelihood estimate, it's this density that we're going to get. But we're still saying the density is consistent across any individual group, that it's not going to vary across groups. But we're saying that the intercept is going to vary across groups. So what we end up with really is this. This is now saying the intercept is a distribution, it's a density across the population, and within each individual group, that intercept varies. So in practice, the easiest way to understand this is a maximum likelihood random effect. It's just a density, it's a histogram, whatever you want. You plot a random effect in any software you want, you estimate the random effect and do a histogram, you're gonna get something that looks like this. This is a Bayesian random effect. Each and every one of the individual groups gets its own density. You can go back and forth from these very easily by extracting the modes across all of these and stacking them back into a latent variable, and then you get a classical random effect. That's why in a lot of software, this thing, the classical random effect, is estimated by something called empirical Bayes means or empirical Bayes modes. They're interchangeable with one another. This is just all of the modes or all of the means of all of the individual groups that the Bayesian model is estimating. Instead of getting the entire density, you just get the maximum or the expectation, the mean, the same way that in this model, you go from the mode or the mean or whatever to a density. You're just transitioning from, do I want a histogram or do I want the mode? Do I want a kernel density or do I want the mode? You're going back and forth. The software is automatically giving you this. In a Bayesian model, the software is automatically giving you this in a maximum likelihood model. But they're interchangeable, assuming you don't do anything with priors, and assuming nothing in the actual estimation of the model goes kooky, which both of those things happen more often than not. But in the models that we're going to do, the toy models, these are going to be interchangeable because we're not really monkeying around with the priors that much in the introductory models. These should not give you different results, noticeably different results, unless you are trying to use informative priors, or at least weakly informative priors. When you start out, or at least when I start by using priors that are going to make the least impact possible and compare them to maximum likelihood to make sure nothing broke. And then I start layering on more informative priors, more useful priors. And what I mean by that is going to become clear when you see the script, because I'm actually going to introduce other kinds of prior structures into this and show you how they make differences. Yes?
So in addition to incorporating priors if you want to, then practically does incorporating this and or go to the Bayesian estimation, right? Does that practically give you? For me, it seems like it's
So the question is, absent priors, if you don't really care about incorporating priors one way or the other, does doing a Bayesian version of one of these models make a difference? Yes and no. So at the very least, you're going to get these densities instead of coefficients, which can be very useful for hypothesis testing. If you do, you can ask different kinds of questions, more nuanced questions about asymmetry and effects. Instead of just saying, does the effect get bigger or not? You can talk about it within a population. There are lots and lots of things that you can do with the kinds of results you get out of a Bayesian model that are just, you haven't even conceived of them yet because they're completely impossible in maximum likelihood and in most frequentist models. That you may not actually want them, but they're plenty possible. You can do lots of things with them. From a more practical standpoint, the software is really your friend. Bayesian models are usually estimated with MCMC, Markov chain Monte Carlo. Maximum likelihood models are usually estimated with some kind of numerical optimizer or closed form calculus or something like that. There's a whole bunch of models you just can't estimate that way. The software will choke and die if you try to include a certain amount of structure in the model. It's going to start giving you warning messages. MCMC and especially Bayes or especially Stan is just going to work much better because it doesn't necessarily care about how difficult the problem is because it's not trying to solve a difficult problem. It's trying to solve tens of thousands of relatively easy problems. So even if you are philosophically agnostic to the differences, even if all you want is the maximum likelihood estimates, especially for multi-level models, it will often be very advantageous to you to go the Bayesian route just for computational ease. If you're going to try and do a Bayesian ordinal logit model, or Bayesian survival models, or not Bayesian, multi-level ordinal logit or multi-level survival models, doing them in a Bayesian context is just going to be like that. It just doesn't care that they're numerically difficult problems. Other software doing it in maximum likelihood is going to have trouble, and it's going to give you suspect results. So we can go to this. It's basically the same thing. Like, we're just transitioning from, are we thinking of these as point estimates to densities? Are we thinking of the random effects as these latent variables where you've got one density for all of the groups? Or are we thinking of them as a bunch of different overlapping densities and you get a different density for each group? Which also is incredibly helpful from a conceptual standpoint, because let's say you're studying students in classrooms in schools. In this version, you've just got the point estimate, you've got the conditional expectation for each individual school. In this version, you've got a whole density to play with, and you can see if something really weird is going on. You can see if that density is bimodal, so that there are two discrete populations within the school that are having different expectations. You can get a lot more information that's just not available to you in a very convenient, easy way in maximum likelihood. What time is it? 3:56, okay. Someone wave at me when we get to 4 o'clock. I'm gonna buzz through these really quickly just so that you're acquainted with what's going on in the rest of the slides. They're the easiest part to conceptually understand at this point, but I still want you to be able to ask some questions in the last couple minutes. So the thing that I want you to do, this is the part about the sheep that we talked about at the very beginning, about not trying to be a sheep, not trying to follow along with just whatever advice the book gives you uncritically. Because as we've already shown, I can give you, like, whatever book you throw at me, I can give you another book that says to do the opposite. I can pull something out of psycholinguistics that says to put 10,000 random effects in your model, and you can't prove to me that it's wrong. Basically, the structure of the rest of the slide deck is to try and go through the different hypothesis-based reasons and data-based reasons why you would want to use certain kinds of models. So hypothesis-based reasons for fixed effects, basically what you're doing is you're hacking out all the between group variants, you're putting those dummy variables into the model. There are specific reasons why you would want to do something like that. If you're trying to do causal inference related work, it could make logical sense. If you don't have very many observations or within groups, you don't actually have to estimate the dummy variable. So it's a nice way to preserve degrees of freedom issues if you can't estimate them to begin with. This is why economists started doing this in the first place, because they had a lot of little groups. So you can't really say that much about group averages when you've only got 4 observations in your group. So it might be useful for you, or at least it might be an appropriate analytical path given the data structure that you've got. But from a hypothesis standpoint, it's basically just about, you don't care about between group variability. You only care about within group variability. You are writing your hypotheses in such a way that you are not commenting on school level differences. You are commenting on within student differences or within classroom differences and trying to control for everything else because that's all you care about. This is most common in an experimental setting, obviously, because that's literally what an experiment is designed to do. It's designed to control for everything else and only talk about the thing that you're trying to measure. And again, I'm just flipping through really quickly. You do not want to make predictions with this model. It will break down in a predictive accuracy model because you're ripping out a bunch of information in your data and you're just focusing on a mechanism. It's like trying to make predictions from an experiment when the treatment in the lab may never actually happen in the wild. So this is an important thing to understand if you're trying to do predictive accuracy, or if you're trying to understand the general data generating process. you wouldn't want to necessarily do this. Lots of people do it anyway because they don't think in these terms. And they're just kind of interpreting, this is what the book says, this is what the reviewer two wants, so this is what I'm going to do. And then they get nonsense. You can have database reasons. You don't have very many groups. Gender, male, female in most studies. You wouldn't have a random effect for two groups. You can in a Bayesian context. Things fragile, but you can do it. But you don't have very many groups. You can't figure out the right way to specify the structure. So the horrible model that I told you you would never actually want to do from the start. A nice thing that you can do is just put in dummy variables for schools or put in dummy variables for neighborhoods or whatever, and section off the data that you're working with to try and fit the models in bits and pieces. So if you want to control for, rip out all of the exchangeability problems of like years being the grouping measure, and you just want to fit the stuff that is consistent across groups, across years, then you would use dummy variables for years, rip out the other part, model the part that you've got left, and then rotate and model the part that you've now ripped apart. So you can pair these things off into different pieces, work on a component, rotate it around, pair off other parts, work on that component, and keep doing that until you've got a much better model. Sociological reasons, you really like making economists mad not to do it. Like an economist is gonna want you to do this regardless. And random effects, basically it's just you care about other things that you can't do with an econometric fixed effects model. You really only want to do this as a standard error correction if experimental conditions are gonna hold. Otherwise, you're going to have to do a bunch of other stuff, right? You're going to have to deal with cluster confounding, spatial problems, network problems, temporal problems, all these potential problems that may just never come up in your own research. Or maybe you just travel back in time to before Hubert-White cluster robust standard errors were a thing, and you really just want to use this as a standard error correction. I think that's possible, right? This is one that I like. You want to do this because you're like me. Sometimes I just bait economists because I'm bored. You just like being yelled at. You don't like other standard error corrections. Not all standard error corrections are made equal. Hubert-White cluster robust standard errors tend to break down if you don't have a lot of observations within your groups. Some people say 25, some people say 50, some people say 100, but random effects just care less about that because they use shrinkage to bring in the group estimates to the mean. So even in small groups, it's less biasing. You've got hypothesis, blah, blah, blah. It's basically just walking you through the rest of the slide deck, why you would want to, in a practical sense, use this particular model. So it's, again, the inverse of the previous. And then I want to show you at the end, blah, blah, blah. I have citations at the back of my slides. So if you want to actually be able to cite the evidence that I'm giving you, depending on the field that you're in, there's stuff from multi-level modeling, there's stuff from econometrics. I've got papers on group mean centering and how that actually works, why that actually works the way that I'm saying it does. Yair Mundlach was the first one that I could find, but other people in statistics and education literature have been writing on this stuff since the 80s at least. So this is a pretty common approach to specifying these kinds of models. It's just in a lot of ways they talk about them in very different contexts, so you don't necessarily understand all the problems interrelate. And then fixed or random effects, lots and lots of different things. Even panel data econometricians, by the way, say you should just use a multi-level model rather than fixed effects. So everyone likes multi-level models. Does anyone have any questions? This is all I've got. Yes?
Everyone prefers multi-level over fixed effects.
Econometricians prefer multi-level over fixed effects. Economists don't, or at least they don't think about them in multi-level modeling terms.
interacted with it.
So Jerry Hausman's a most famous panel data econometrician, or one of the most famous. He wrote the Hausman test. His paper from 1981 is a multi-level model. It's the Hausman-Taylor model. You've also got pretty much every book on panel data econometrics teaches multi-level models. They just don't call them that. So there's a language disconnect between economists not realizing they're talking about Hausman-Taylor models and everyone else talking about multi-level models. A multi-level model, in my mind, is a model that both includes a group varying intercept, maybe group varying slopes, also probably group mean centering, so including group means to deal with cluster confounding, maybe also including some other things. So it's a properly specified modeling structure in a data generating process model. It may or may not have the parts as needed in a particular analysis. Some people call those mixed effects models, by the way. I use multi-level because it's the first term that I heard when I was learning this stuff. If there are no other questions, then we're going to take a 30-minute break, and the people who haven't been scarred for life can stick around and learn how to actually do this stuff. Otherwise, have a wonderful day.